So actually we made the structural analysis and design of some elements in our previous section, we had here the I sections or the HEA section for the railway crane. So it will be interesting to design them. First of all, I will just select them. I will select them and see them in a new window alone. So edit in new window. These are my HEA sections to be designed. Their name are 61, 62, 34, 5, 6, 7, and 8. As analysis is done, you have here the green button means that the results are available and are up to date. You have to go here to the steel design, steel aluminum design. We'll define firstly a new group with the member list. So we close the previous window. The member list 61, 2, 3, 4, 5, 6, 7, and 8. 61 to 68. And this is a new section, 61 to 68. Number of the group is 1. Name is Railway Crane or Crane Railway. Material is S355. You can change here if you have different material. So this is a group 1, Crane Railway with the members 61 to 68. Okay, or save. Okay, then we have here to make the members verification per group. Group 1, have only one group. Group 1. A design according to the ultimate limit state involving all the load cases 1 till 10. Calculation. So as I think that the section is not enough. 200 millimeter for this crane of 10 tons is too small, with a ratio of 2.19. So it means it's 120% not safe. Now we have to change this section. Have here a calculation note if you want to check which is going wrong. You can check this calculation note. So PR, combination of axial and moment along Y and along Z, MY and MZ, having a safety coefficient of 2.19. So this is the main load. We have to change the section. Let me check something, please. So if you go back to the section, and let's try HEA 300, for example. affect this section for all this element, all this element. Or if we, as we made a modification of the section, the results are all out of date, we have to run them again. And we'll go back to the steel design. Now the same group, we have to make a code group verification. Now calculation again. The ratio is 0.58. So now the section is safe. 300 is okay, but with a 42% of safety. So it means maybe the adequate section is between 200 and 300. We'll check the second method of design by code group. Again for the group number 1, calculation. Now it gives you directly the adequate section. So the software tried 300 firstly, it was safe. It tried 280 safe, 260 safe, 240 unsafe. And then it tells you that the adequate section, the most suitable one and most economical one having the lower safety factor is the HEA 260. You can now ask the software to update this section, change all. So this is the second method of design. You can select the design by you can just make the verification, so you will change manually each time the section, or you can ask the software to make the design. So using the family HEA, so you will define only the family of section in the data entry of the software. Then if the section is too safe, the software will try to decrease the height till having the section with the minimum safety factor. So here we have the logo is okay, this is the most suitable one. And if the section was unsafe, the software will try to increase the height till reaching an adequate section. So now you can ask to change all. And your section, you can save this calculation, save or not. And now if you check this section, right click, object properties, it's HEA 260. It was changed automatically. As you change the section, you have to repeat the analysis because the internal forces diagrams for the HEA 300, the design was made on the HEA 300. You change the section now the self-weight is different, the behavior of the element under loads is different. So you have to update the internal forces diagrams and to repeat the design again. So now the safety factor is a little bit different because data entry was updated. And now the section in the data entry is 260 and the adequate one is 260. So you don't need to make any changement anymore. So this is for and again you can, so I will repeat, you have to generate the calculation note, full one, and you have to save this calculation note as PDF or any format you like to use it later in your appendix of the report. So talking about the printout of your annex of your report, you remember in my previous session we have some issues with printing the Corbel design report because the printing was done directly to the printer. I didn't have here the option to save as PDF or print as PDF. We can solve this issue by going to the Windows, to Devices and Printer, and let not the printer, this is my printer at home, Xerox Phaser. Sorry, this is my printer at the university, this is my printer at home. So you can let this Adobe PDF set as by default printer. And now if you print any document in your Windows, it will be printed directly as PDF file. You will have a file. Again, going back to my structure. So we designed the columns, the beams, the steel beam here, the corbel. We can, for sure, we can design the foundation, selecting one node here, the support, and going in the same manner to the RC element design. You will have to select the simple cases here in the RC element design. The software will make the combinations alone. So this is my foundation. This is my node. There's different sections, different dimensions. I will go back to try to figure out which node I am working on. This is node number 22. So node number 22, go to RC element. So foundation 22, I am focusing now on this foundation. I will keep the by default proposition of dimensions as is, check if they are adequate or not. I can change as the previous design, the calculation option, the reinforcement pattern, to check the specified type of dowels and shapes. Maybe this one is more interesting. Dowels, stirrups, closed stirrup like this. Splice. Okay. And you can again change the geotechnical options to know the stresses, the allowable stress, 0.3 megapascal, or different according to the soil report, the properties of your soil. Safety factor for the rotation, for the moments, for the capacity, settlement. So you have to specify here all your code safety factors, the property of the soil, in order to design well your foundation. Then you can generate the calculation. Problem is reinforcement arrangement. So as you have a problem, you will not be able. So this is just a warning, it's not an error. So you have maybe too much reinforcement. You will try to find a solution when you will go to AutoCAD. Here is the calculation note for your foundation, for your isolated footing. And of course, you can generate calculation drawings. You can generate detailed drawings with the reinforcement of your foundation, of your footing. Here are the dowels, the main bars. So probably we have here, probably the load is not compatible with the soil property. You have too much reinforcement. I don't know honestly what is the type of the soil you will take 0.3 megapascal. It's maybe acceptable. It again. Okay. These are the results, the axial, the MX, MY to design the footing, the pressures are around the footing, the average settlement, capacity, contact surface, etc. So you are more familiar than me with these terminologies for the design of the footing and how the footing is designed, how it's checked, etc. So I will go back to my structure. You can design all the footings here. You can we can look again to our slab at the roof. Usually we are trying in this project to make an application of our RC3 project. So I strongly recommend to design the roof of the hall using the inverted T or using the ledge beam and the double T beams. So let's try to see how it will be done. We can here replicate the corbel at the top of the roof. The corbel will support a ledge beam here. Then on the ledge beam we'll place a couple of double T beams. So let's try to make this operation. I will take just this part of the structure alone. And then I will delete these beams. I will make a copy for the corbels. So I will copy the corbels from here to here. Then I will link the corbels at the top with a ledge beam. So actually here in Robo we don't have beams with L section. You can consider that it's a rectangular beam. Then in the design we'll take into consideration the exact shape of the beam. Let's say I don't know, you have to check. Let's say it's width of 40, depth of 60. It's just a trial section. And I will link so the corbels with this ledge beam, assumed ledge beam, it's a rectangular beam. So it means if you are modifying the slab like me, you must go to the roof level, delete the loads on the roof level, delete the diaphragm, Then specifying the diaphragm again with the new elements, the ledge beam, the corbels, and applying again the load on the new elements. So these beams will be copied to the second side. We have now the elements resting on the corbels, acting like a ledge beam. And then between this ledge beam, we have to place our double T beams. It's a system of precast elements. To have just an idea about the dimension, you have to use one of the catalogs of the precast concrete industries, like, for example, a catalog of a factory in United States. So PCI design handbook. Now my span is around 12 meters. The span of the beam of the beam here is around 12 meters. So considering the beam is simply supported, 12 meters over 16, as calculated previously, is 750 millimeters. Over 25 is 30 inch. 30 inch. We'll try just to figure out what is the geometry of the double T beam having a width, having a total depth of 30 inch. So we have here a catalog. So we are looking to a double T having a total depth of 30 inch. Don't have 30 exactly, we have 24 or 32. Well, let's use this depth of 32 inch. It means that the depth is 32 times 25 is 800 millimeter. In this case, the total width will be equal to 8 feet. 8 times 12 times 25 is equal to 2.4 meters. So again, we'll try to see if in robot we have a double T section. We'll try to use this geometry. Again, this one is for, in reality, it's a pre-stressed concrete section. If the section will be reinforced concrete, so the depth must be higher, but actually we'll keep as is. We'll try to define a beam section, RC beam. We have here the T section, so we'll take only one T having a depth, a width of 2.4 meter or 1.2 for 1T. B flange equal 120 centimeter. B equal 4 3/4 to 7 3/4, so 7.75 plus 4.75 over 2. Average width is 7.25 inch times 25, 156. Let's say it is equal to 200, because as I said, it will be an RC section, not a preset section. So 20 centimeter. Total height is 80, and height of the flange is 2 inch. And for the same purpose, I will take it 10 centimeter, 100 millimeter as a trial section. So this is my T section. say Flange C35. And then I will create T-beams all over the area of this panel. Each T-beam again is 1.2 meter. So you have to proceed step by step. You have to proceed carefully. So if we draw firstly a T-beam, the section from here, or we can start here from this end to this end. This is my first T-section. It's shown it's a T-section. Now the T-section must be duplicated from center line to center line. We must have center line to center line have 4 feet or 1.2 meter. So we have to take this beam and to make copy each 1.2 meter along X. The vector is 1.200. Number of replication we have to calculate in order to know the number exactly. So I don't know actually. Let's try to have an idea about the approximate number. Span from center line here to the center line here have 19.74, 19.73 over 1.2. We must have 16.5. Let's try 17 repetition. So we ended with one outside. Have to delete it, and don't forget the opposite node. Okay. If we show the sections, approximately we covered all this area. As now we created just elements without node intersection. We have here to select all and to make the intersection in order to connect these beams, at each position to the ledge beam. So to have here node, this node 130 is only for the T section. It's not for the ledge beam. In order to have here a common node, we have to select all in this window and to make the intersection. Actually, have here common node between this element, and this element. So now the system must work. We have to check again if the diaphragm is well defined. I will go back to my first initial view. Deep XZ view, select all this level, edit in new window. As shown, the diaphragm still working. If you have any doubt, we can define it again. Diaphragm. You can click here on delete and select. I am just trying, don't know if it will work or not. Yeah. It's working. Then selecting again the diaphragm with a master node and all the nodes. Now we are sure that the diaphragm is connecting all the elements in this level. Don't have any doubt. The system at the top is a double T or T resting on ledge beam. Unfortunately, we don't have a L section in Robo, so we'll take it just as a rectangular, and it will be designed in the our famous mini software, the RCM ACR builder, will just make data entry here for the shear due to dead, due to live, and you will get the additional reinforcement. So I am saying additional reinforcement because the main reinforcement will be generated by Robo. Are taking here just the kind of load which is couple of concentrated loads. Can be couple of concentrated loads or can be uniform load. Functioning of your data entry. So here calculate bar spacing. Okay, so this is for the ledge beam, and as I said, you will design the beam from Robo. So taking, for example, a view, deep view XY, you have to run again the calculation. Isolated node. I have one isolated node. I didn't delete. So isolated node here. I have a node alone. I must take and delete. Repeat the calculation again. Node 86, we have instability. Where is node 86? So node 86, somewhere 88. Node 86 instability. It's strange because we didn't touch this part, so we can ignore this warning. So as I said, we can look to the deep XY view to select this beam, sledge beam entirely. And to take it to the RC element module to design the corresponding reinforcement, and the additional one will be provided by the RCM ACI builder. The T-beam must be designed again by Robo. You can try if you want. And that's all. I think that we covered everything. This part of floor can be designed in Robo, but it will be much more easier to design in Safe. If you don't know how to manipulate Safe, you can design it manually. That's all for this project. Hope you will enjoy. If you have any question, please refer to the steps shown in the video. I think that if you follow carefully, you will proceed without any difficulty. If you still have some issues, we will discuss and we'll try to organize a Zoom session later when you need to answer all your questions. But chatting by WhatsApp will not be an efficient tool because we are talking about a software, about a specific model for each one, and I will not be able to figure out what's going wrong in your modeling. Again, hope you will enjoy and have a nice project. Thank you.